All right? So we've got this scatter plot here with a line of best fit, and they gave us an equation for that line of best fit. And it models the relationship between the price per pint of a pint of raspberries, and then how many pints they sell on any given week. Okay? Each dot represents a week. There are 19 dots. So how many weeks do you think they tracked this? 19 weeks. All right, now, according to the line of best fit, how many pints of raspberries would the grocery store expect to sell when the price was $4.50 per pint? How could I could estimate by looking at the line of best fit and see, like, okay, my answer is going to be somewhere around 90. But if I want the exact value, I need to plug it in. Y is 233 minus 32 times 4.5, which gives me 89 pints. So 89 pints of raspberries sold at $4.50 per pint. Okay? That's part A. Part B. For how many weeks was the 19-week, of the 19 weeks shown, was the number of pints sold greater than expected? What would I look for on the graph to find that? Yeah. This line says, hey, this is what we expect to sell. Anything above it is greater than expected. So how many weeks was that? 8 weeks. Okay? What is the best interpretation of the meaning of the slope of the line? What is the slope of the line? Yeah, so it talks about demand. So what is the slope? What's the specific number represents my slope? Negative 32, okay? So my slope is negative 32, okay? So in general terms, yes, I'm talking about the demand of the raspberries, okay? But let's get a little bit more specifically about the trend, okay? When something happens, something else happens. What is that relationship between pints and cost? Pints sold and the cost per pint. Yeah. When price increases, quantity sold decreases. Okay? Quantity sold decreases by, looks like 32 pints per dollar. Okay? Decreases by 32 pints per dollar. Questions on the scatter plot? And what we're going to be doing today is we're going to be reading graphs and charts. Okay? It's reading graphs and charts, and it's using critical thinking to analyze it. There's not going to be that much calculation involved. I mean, that's kind of the extent. That's most of what we're going to see. It's going to be, can you read the data presented and make inferences or determinations based on what you get? So that's our interpreting relationships. All right. So here I have a table, gives initial number of bacteria placed in a growth medium and the number of bacteria in the growth medium over 3 hours. So here's the start, and then after 1 hour, 2 hour, 3 hours. How much bacteria was in the growth medium after that amount of time? 1.0 times 10 to the third is what number? Not 100. 1,000. All right. 4.0 times 10 to the third. 4,000. 1.6 times 10 to the fourth. And then 64,000. Okay. So we have two types of relationships that we're going to be looking at. Linear and exponential. Linear relationships increase by the same amount every single time. You're adding the same thing over and over and over and over and over to get one number to the next, to the next, to the next, to the next. Exponential is multiplicative. I'm multiplying by the same amount over and over and over. So I take the previous number and I multiply it, and I keep doing that multiplication over and over and over to get from one to the next. Exponential growth is significantly faster than linear. Okay? Linear growth is a straight line. Okay? Or like the scatter plot we saw. Straight line. That's linear growth. Exponential is the number gets a lot bigger a lot faster. Okay? So does this model linear or exponential? It's getting a lot bigger. I increased by 3,000, then I increased by 12,000, then I increased by 48,000. Okay? I'm multiplying by 4. So it's an exponential growth. So looking at those values, that exponential increase, which of these two equations can I eliminate just knowing that it's exponential? I can eliminate B, what else? And A. Both of those are linear relationships. How do I know that they're not exponential? They're missing what? An exponent. There's no exponent. So these are the only two possibilities. So right off the bat, seeing that relationship, boom, two of my answers are gone. Okay? Now, knowing your relationship with exponential equations makes this a little bit easier for picking which one it is. All right? One of these is growth and the other one's decay. Okay? My numbers are getting bigger, so I'm going to choose the one that has the positive exponent. All right? Because my numbers are getting larger. They're getting exponentially bigger. If they were getting exponentially smaller, then I could choose C. Okay? If that change was becoming, the change from one to the next was smaller, I would choose C. Okay? But if you're not sure, and you say, well, I don't know which one it is, take a value of T, plug it into the equation, and make sure you get the correct output. And you can just do a quick evaluation. Okay, I think it's this one. Let me evaluate this. Boom, it checks out. It works. So you can always take one of your values, plug it in. Once you eliminate some of the ones that you know it can't be, make an educated guess on what you think it is, and then test it, and then move on. Okay? So this is an exponential growth. All right? A bank has opened a new branch as part of a promotion. The bank branch is offering $1,000 certificates of deposit at simple interest of 4%. Simple interest is one of our two types of interest. Simple interest is linear. You invest an amount of money, they say, okay, for this amount of money, you'll get, I don't know, $5.30 in interest. And then every month we'll give you another $5.30 over and over and over and over and over again. So they're adding that amount to your account over and over and over. Okay? So the amount of interest you're getting isn't changing. You just get that same amount repeated. Okay? So simple interest is linear. There's a couple formulas you need to be aware of. To find simple interest, just the interest is principal times rate times time. So the amount of money you invested, what's the rate of the investment, and how long do you have it in there? That tells you just the interest, how much money you're going to get. But if I want to know the amount in the account, well, the principal that I put in there counts towards my balance, plus any interest that I earn. So when I substitute this, we get a formula that we see more often with simple interest. And that tells me how much money is in the account at any given time. The amount of money I invested plus all the interest I earned up until that point. And then to make it a little bit more common or annoying, depending on your point of view, okay? Instead of having P plus PRT, we factor out that P. And you'll see this one even more often. This is the most common form of that formula. Okay, so for simple interest, the amount is going to be the principal times 1 plus the rate times the time. Okay, so P times 1 plus RT. So that's my formula for simple interest. Well, this is kind of all the getting to it, but both of these are the formula for simple interest. This is for finding simple interest. This gives you the amount in the account. Two forms of the same equation. Okay, two forms of the same equation. Now, so I want an equation that models $1,000 principal, 4% rate over any given number of years. Which two of these can I eliminate to start with? C and D, because they've got exponents. And simple interest is linear. So now what I need to do is figure out which of these matches more closely. B. That is 4%. Well, so this doesn't have the 1 plus. Okay, this is 1 time. So this is a weird amalgam of simple and compound.
So would it be the same? Oh, yeah.
This, all this is going to do is tell you how much interest you earn. It's not going to give you the full amount. So, I don't want that in there anymore. Okay? And again, kind of look and fill in what we have. I know this should be my formula. So my amount needs to be 1,000 plus, 1 plus, my rate is 4%, and I don't know time. So we just use some variable for time. They use K, our formula uses T. We don't know what it is. Okay? But then, boom, that matches up with my equation. Okay? Simple interest is linear. Compound interest is not linear. It's going to be exponential. Okay? So the formula is a little bit different. But again, I can eliminate A and B because they're not exponential. All right? Compound interest. The amount in the account is the principal times 1 plus the rate over the compounding frequency raised to the power of the frequency times time. So that's our formula for compounding interest. And the way compounding interest works is, okay, so every month they give you they take that amount and they add it to your principal. So every time you get interest, it's going to be a larger amount every single time because your principal's going up every time you earn interest. All right? So looking at the stuff that we have here, we can fill in some of this information. Again, I have $1,000 principal. My rate is still 0.04. Okay? But now N. N is my compounding frequency. Okay, so we look and we see we have an interest rate of 4% per year, compounded semi-annually. How many times a year is semi-annually? Twice. So my compounding frequency is 2, because it compounds twice. When I simplify this part in the middle, okay, half of 0.04 is 0.02, add it to 1, I get 1.02. And then K instead of T, because why keep the variable the same? That would make too much sense. Right? So it matches up. Now with our compound interest and our simple interest, again, simple interest is linear. Compound interest is exponential. And being able to compare those different types of growth. You need to be familiar with the formulas and be able to recognize them. Okay? Recognize what they should look like. Do not assume they will be provided for you. They might not. I hope they are, but I don't know for sure. Okay? The only ones I know for sure that show up are the geometry formulas when you need area. Okay? I'm pretty sure they don't include interest, simple interest on there. You need to be able to recognize the linear relationship and the exponential relationship. All right, last one I want to look at is this graph here. So each evening, Maria walks, jogs, and runs for a total of 60 minutes. The graph above shows her speed during that time. Which of the segments represents the time when her speed is the greatest? So where on the graph do I need to look to see when her speed is the greatest? Point all the way at the top. because our y-axis represents our speed, so I want this point up here at the top. Okay? What is her greatest speed? 8. Okay? All of these are ordered pairs on that graph. Okay? They're all ordered pairs on that graph. So we need to look at a couple things, make our life a little bit easier. All right? Her greatest speed is 8. That's our y value, right? Is that her greatest speed? Is that her greatest speed? I can eliminate all of those. I only have one option left. B. It also matches up with the time at about 20 minutes and at about 35 minutes. So seeing the points where our desired result is, and then matching it up with what options we have available. It's a segment from 19.8 to 35.8. That's what these 2 points are. This is the point 19.8 and 34.8. Just those 2 points on there. So a lot of what you're doing with your assignments tonight is reading and interpreting a graph, a table, or an equation. What it means in its context. So you need to make sure you look really carefully at the information that's presented and see what option it best represents. Okay? Questions, comments, concerns? All right, cool.